Alright, so now in this problem, we are given a binary tree and our task is to basically invert it, or in simple terms, just mirror it. So that means for every node in the tree, we will need to swap its left and the right children at every level, right? Basically, this operation should be applied from the root to every child node, right? So let's actually visualize an example to make it clearer. Now in this example, if you see, before the inversion, the tree looks like this, right? And after inversion, it becomes like this, right? So you can see over here how every left and the right child pair is flipped throughout the tree, right? So 2 and 7 have been swapped with each other to become 7 and 2, right? Similarly, under 7, 6 and 9 have been swapped with each other, right? And 1 and 3 have also been swapped with each other, right? So that's what we need to do. We need to just invert the given binary tree. Now maybe you can just pause this video and try to think of a solution. And once you are done, you can just come back and check the solution here. Okay, so now to invert a binary tree, we will use a recursive strategy, right? So the idea here is that for a given node, starting from the root of the binary tree, first of all, we will just swap its left and the right children, right? And then after swapping the left and the right children of the current node, we will recursively do the same thing on the left subtree and then entirely on the right subtree, right? And this way we will end up mirroring, or rather inverting, the structure at each level and ensuring that the final output is a complete mirror of the original tree, right? So that's the intuition we are going to follow. Now maybe let's break this down into step-by-step logic, right? So first of all, we start at the root node, and if that node is null, or if it's a leaf node, then we just return, as there is nothing to swap really over here, right? Otherwise, we first swap its left and the right children, right? And then we recursively invert the left subtree in the same manner. And after inverting the left subtree, then we recursively invert the right subtree, right? And finally, we just return the node after the inversion is done on it completely, right? So that's the entire solution. Now maybe let's walk through the inversion process visually on the example tree. So if you see over here, we start at the root node, which is 4, right? Now we swap its children, so 7 becomes left and 2 becomes right. Now we move to the new left child, which is 7. We swap 6 and 9. Now we visit 9. And since it is a leaf node, we have nothing to swap really and we simply move back, right? Now we visit 6, which is another leaf. So we simply return again. Now we again come back to the root after inverting its entire left subtree. And now we process its right child, which is 2. And we swap 1 and 3 with each other, right? Now we visit 3, which is a leaf node. Then we visit 1, which is another leaf, right? And that's it. We have visited and inverted all the nodes of the binary tree at this point. And now we can simply return this inverted tree as the final output of our function, right? So that's the entire solution. Now maybe let's walk through the Python implementation of this logic step by step, right? So first of all, we define the tree node structure in this node class over here, like this, right? Now we define the invert tree function, and inside it, we first of all handle the base cases. That is, we return the node as is simply if it's null or if it's a leaf node, right? Then we simply swap the left and the right children with each other over here, right? And now after swapping the left and the right children of the current node, we now apply the invert tree function recursively on both the children, that is the left and the right separately, one by one in this manner over here. And finally, after inverting the current subtree, we just return the root with the updated structure, right? So this is how we are able to invert the given binary tree in place and efficiently, right? Now maybe let's see the time and the space complexity of this solution. So since we are visiting every node exactly once over here in this particular algorithm, the time complexity will be order of n, where n is the number of nodes in the tree, right? So it will be linear. And the space complexity will be order of h, where h is the height of the tree. And this is due to the recursion stack that is created as a result of the recursive calls to the left and the right subtree at every node of the tree, right? So that's the entire solution. I hope you understood it well. And now I will see you in the next problem. Happy coding.